The alternating property is now much less work. Namely, assume we have two different vectors. So we have two different row vectors which coincide. So assume there exist I and j between 1 and n with I not equal to j and ai equal to aj. Okay, then it particularly follows for the row vectors that if you multiply now both rows with b, we also, of course, get the same thing. So ai times b is equal to aj times b. This implies db of a, now I'm writing the rows again, a1 to an. This is now the 1 over det b times the determinant of a1 times b to a2, to an times b. And now we see that two of them, aib and ajb, coincide. But here we now, you can use that the determinant is alternating. So here we really have an honest-to-God determinant where two of the inputs are the same. So this must vanish then because that is alternating. So here, that alternating. So this is 0, and then of course the whole thing becomes 0. And this is the alternating property for dB. Good. Okay, now the normed property. So dB, if we enter the rows e1 to en, the canonical basis of k to the n. Now the canonical basis here, this is just the matrix which has this as rows. It's very simple, it's just the identity matrix. So as a matrix, this is the same as dB of the identity matrix of size n. And now if we insert the definition, this is det of in times b divided by det b. But we know that multiplication with identity doesn't change anything. So in times b is simply b, meaning we get det b over det b, which is certainly 1. So this property is satisfied as well. dB of this canonical basis is just 1. Now, we've shown that this has the properties of the determinant, and by theorem 9.8, it follows that dB must be the determinant. So dB of A is det A for all A in M n by n k. And so this implies what we wanted, det of AB. If we write this down explicitly and bring det B to the other side, this is det A times det B. This is what we wanted. So this proves the product property in this elegant way by just showing that this has the defining properties of a determinant. Okay, now let's derive some consequences. This product property is something that is very, very, very useful, and we will see also later why. But first let us derive some nice computational rules that we immediately get from this product law for the determinant. First of all, if A is invertible, so if A is in GL and K, then the determinant of the inverse matrix. So far we have no idea. I mean, if we have a matrix and want the determinant of the inverse, we have a method of computing the inverse and then doing that. This is very long and tedious. This now tells us the determinant of the inverse is simply 1 over det A. So, as easy as that. Now, second part that's important, that A and B be two quadratic matrices of the same size. And assume we have some invertible matrix which I call P, such that B is equal to P times A times P to the minus 1. Then it follows that A and B must have the same determinant. Okay, this now looks quite arbitrary. So yeah, okay, I mean, two matrices could be related like this, but why should they? So why should we have such a matrix P? In a bit, we will see where this occurs, namely with respect to matrix representations of endomorphisms. We shall see this in a bit in the end of this section, but this is, just keep in mind, this is really useful and important. Now, how to see this? This is now an immediate consequence basically of the previous theorem. Namely, we start with A, so we know that, so the inverse by definition is A times A to the minus 1 is the identity. So we get from theorem 914 1 is the same as the determinant of the identity. This is what we've seen. This is upper triangular, only ones on the diagonal, so it's 1 times 1 times 1 times 1 and so on. This is 1. So this is the same as that of A times A minus 1. And now we can use this theorem 914. It's getting in precisely here. This is the same as that A times that of A to the minus 1. And now we just have to divide by that A and that's it. So this immediately follows. Okay, part B. So here again by theorem 914, we get the following. The determinant of B is by definition the determinant of P A P minus 1. And now we can use the theorem twice. So first of all, this is the same as that of PA times that of P to the minus 1. And then we can use it for this again. So we get that this is the product of all three determinants. So this is that P times that A times that P minus 1. But now we can immediately use A. So this is the same as that P times that A. So this here is the same as 1 over that P, so divided by that P. And of course, we can now cancel these two that P's. This is invertible, so this is non-zero, it's fine. Everything's well defined, so the result is that A, and this is what we wanted. And we're already done. Okay, so this is a nice consequence of that. Now another nice consequence is that we get a nice group property on an interesting set of matrices. I had some hybrids of corollary of theorems and definitions before. Now it's the first hybrid of corollary and definition. 916. Okay, we consider the following. SL of nk is defined simply to be the set of all A in M n by nk, so all quadratic matrices such that the determinant of A is equal to 1. Whoops, almost unreadable here. That A equal 1. So all matrices of determinant 1. Of course, if the determinant is 1, it's non-zero, so all matrices are invertible. This is something that we get for this, but this is the definition part. I want to introduce this term here, SLNK. And it turns out then SLNK is a group. And now with what multiplication? Of course, matrix multiplication. So with respect to matrix multiplication, and it has a particular name, where this is why the S is there, called the special linear group of degree n over k. Oops. Okay, this is the special linear group. So it's a subset of the general linear group. This is something more special. The general linear group was just everything where the determinant is non-zero. So this is really a part of it. Okay, now how to see this? So first of all, we need to show that, we know that by, this is what I just said, theorem 912, sorry, that the determinant is non-zero, so the matrices are all invertible. SLNK is a subset of GLNK. So to make this a group, we first need to see that this is well defined in the sense that this contains all products of elements. So if I take two elements of SL and K, I take the product of them. This is again in SL and K. And if I have a matrix in SL and K, the inverse must be in there. But for this, we can just use the previous results. This is something very easy to see. So by theorem 914, we get for all A, B in SL and K that the determinant of AB is the determinant of A times the determinant of B, which are both 1. So this is 1, and thus AB is again in SL and K. Okay, and now for the inverses, this is now by corollary 915 part A. If A is in SL and K, then det A minus 1 is just 1 over det A. This is 1, so we have 1 over 1, which is 1. And so the inverse is in there again. Okay, so it's well defined with respect to products and inverses, and that it has the group properties, the multiplication there, so associativity and so on. This follows as for the multiplication here with the group properties on GL. So group properties follow, I'm not very precise here, but they follow from the group properties of GL and K. So you could check these properties again, but the important part is now that this is really well defined in that sense, so I won't care too much about that. So this is just a standard computation. So we see this is indeed a group. Okay, now another interesting property of determinants of matrices is how they behave with respect to transposes of matrices. Sorry. This is now theorem 917. The following, that n in n and A be an n by n matrix, then the determinant of the transpose of the matrix, that of AT, this is simply again the same as the determinant of A. So transposition doesn't change the determinant at all. Okay, now as for the proof of this, I'm going to leave this to the lecture notes, because this is some very explicit computation with regards to these components and the permutations. You take the explicit formula of that and really do some computation with these permutation maps. So the proof is contained in the lecture notes. So this is everything. So it's not very insightful, so it's really a long but straightforward computation. Okay, that's another nice property. Now, so this is basically most things we need for determinants of matrices so far. I said also in the headline of this chapter that we want to study endomorphisms and to see determinants of endomorphisms in that sense. And this we do by studying determinants of matrix representations. And for matrix representations, we need to see, basically if we take an endomorphism and take a determinant to be the determinant of a matrix representation, this matrix representation, of course, always depends on choices of bases. So we need to make sure that we can define a quantity which is not depending on a basis, so which is independent of that. And for this, we need a few little preparations, but this is not too hard what's coming now. Okay, namely, first of all, a definition, some new terminology, definition 918. The following, that n in n and that A, B be quadratic matrices, n by n matrices. A and B are called similar, and it depends on the book. Some also call them conjugate, but I prefer the term similar because later on we will see also complex matrices, and there it's easy to be mixed up with conjugation and complex conjugation. So I prefer the term similar here. They're called similar if, basically, if we're in the situation of this corollary. Namely, if there exists some P in G, L, and K such that B is equal to P, A, P minus 1. So this strange situation, which is not at all apparent what this is good for. Okay, I will now erase the board and then tell you what similar matrices have to do with matrix representations of endomorphisms, and so getting back to matrix representations, and then see how we can use this now to then define the determinant in a bit. Now we're studying endomorphisms. We start with a finite dimensional vector space over K, which I will call V as usual. And I call N its dimension. And I consider F to be an isomorphism. Endomorphism. F from V to V, an endomorphism. So just a linear map where these spaces coincide. Now, if I want to study matrix representations, I have to, usually if I have a general linear map from V to W or something, I need a basis of V and a basis of W. And can then describe my matrix representation with respect to these bases. Now, if I have the same space here, there's a nice construction I can do. I can just take the same basis on both spaces, because it's the same. So I can just take a basis B here and the same basis B there and consider the matrix representation. And this I will just introduce some new notation. I will just write it down like this because this is a bit not enough for an own definition. For a basis B of, an ordered basis, an ordered basis B of the space V, we do the following. We just write MBF, and this is notation for MBBF. This would be the matrix representation of F with respect to B on the domain and B on the codomain. And we just save one B by writing this. Now, V is an n-dimensional space, so it's a map from an n-dimensional vector space to an n-dimensional vector space, which means the matrix is an n by n matrix. Okay. Now, so we take, keep in mind, this is basically taking the same coordinates in both domain and codomain, so very roughly. Now the question is, if we decide to always take the same basis on both things and now change the basis from B to some basis C, what happens? And the good news is, from the determinant point of view, nothing very serious happens. This is theorem 19? Yes, 19. Theorem 919. So V, finite. If V is a finite dimensional vector space over K, F is an endomorphism, and we have two different bases. B and C are ordered bases of V. Then we have two different matrix representations, namely MB of F and MC of F. And it turns out they are similar, as in the previous definition. So we get an invertible matrix, so that multiplying with the matrix from the left and with this inverse from the right, we would go from one matrix to the other. Now, how do we see this? This is actually just writing down something we already know. Namely, we have seen how to compute, if we have different bases, how to transform the different matrix representations into one another, namely by just using these transformation matrices, which were basically these basis change matrices. And this is what we do here as well. Namely, so proof, so n is again the dimension. So we take TBC be the transformation matrix, I forgot something. This is the transformation matrix, and this is, we've seen that transformation matrices are always invertible. This is so in GL and K, be the transformation matrix from B to C. Okay, and then we've seen how to convert these matrix representations into each other. That was theorem 826. Namely, we get the following. The matrix representation MC of F. So we have always done this with two different bases, so let me expand this notation. This is MC, C of F. Now, if we want to start with MB, B of F, so take B on both sides, we need to multiply from the left with the matrix which turns B into C, which is T, B, C. And here we also have B and C, so we need to multiply from the right with the inverse of the matrix which goes from B to C. So T, B, C minus 1. This was precisely that theorem. And this now looks as P MB of F times P to the minus 1, where we just put P to be this transformation matrix. And this is all we needed to show. P is invertible. This is just by definition of similarity. This means MBF and MCF are similar. And this is what we wanted. So this is good news. Namely, this means we can now define the determinant of an endomorphism by not taking arbitrary matrix representations, but matrix representations of this form where we take the same basis on domain and codomain. And we see this doesn't depend on B or C. If they are similar, they have the same determinant. This is what we have just seen in this previous corollary. So this means this determinant is independent of the choice of basis, and so we can define this really as a number we associate with F itself, not with the basis, just with F. Now, so this is definition 920. So that V finite dimensional vector space over K. F should be an endomorphism. Then we define the determinant of F, this is what we call it, of F. Now, we first had the determinant of vectors, then we had the determinant of a matrix, now the determinant of a linear map, so of an endomorphism. So this is det F, which is defined as the determinant of the matrix representation MBF, where B is any ordered basis. So where B is an ordered basis of V. And we've seen, so by this theorem about similarity, so theorem 919, and corollary, corollary 915b, corollary 915b, I hope this was correct. My notations are a bit messy, okay. My notes are a bit messy. So by theorem 919 and corollary 915b, that MBF is independent of the choice of B, hence that F is well defined. Okay, so this is the determinant of an endomorphism. Just go by the matrix representations and take the same basis on both sides of the map. Okay, now I want to conclude this section by just giving a theorem where I'm just stating basically what follows about determinants of endomorphism from what we've already seen about determinants of matrices. So we can use them to really get results about endomorphisms. And all these things that I'm now going to write down are just reformulations of previous theorems, and I'm not giving down a reference each time, I'll just explain what goes on there. And the proof with the correct references is contained in the lecture notes. So here I'm now going to do just the proof. So theorem 921. Oh, not again. V is a finite dimensional vector space over K. F and G are supposed to be endomorphisms, so linear map from V to V. Then we have the following properties, and this is now a collection. And with each property I will I'll explain to you why. First of all, if I take the determinant of the identity morphism, this is clearly a linear map going from V to itself, so it's an endomorphism. What is the determinant of this? It's simply 1. And why? If I take the identity matrix and represent this with respect to any basis and take the same basis on domain and codomain, I always get the identity matrix, so IN. And the determinant of IN is 1, so the determinant of the map is 1. This is all we need. Okay, B. F is an automorphism, so an endomorphism which is an isomorphism. If and only if that F is non-zero. This follows since we've seen that a map is an automorphism if and only if the matrix representations are invertible. So this is, by an invertible matrix, so this is about what we know about invertible matrices. It's invertible if and only if the determinant is non-zero, and so the same property follows for F. So this is just reformulating this in this concise way for F. Okay, C. The determinant of the composition. So if G and F are endomorphisms, the composition is an endomorphism again as well. So what is the determinant of this? We've seen that the matrix representation of a composition is by definition the matrix product of the two. And we've seen the determinant of the product is the product of the determinants. So in our case, this means the determinant of the composition is also the product of the determinants, simply by going via the matrices and taking a look at their properties. Okay. This is the case, and D, now another property that we have, if F upper star is the transpose. The transpose is a map going from V star to V star. Now, V is a vector, is a finite dimensional vector space of dimension n, then V star is a vector space of dimension n as well, as we've seen before. And the transpose is again a linear map going from this space to this space, so it's also an endomorphism, just of a different vector space, namely of V star instead of V. So if this is the transpose of F, and here we again need what we know about matrix representations. We've seen that if we have a map F and we have the transpose, then the matrix representation of a transpose with respect to a dual basis is the transpose of the matrix of the with respect to the original basis. And so we see in the matrix representation, only depend on each other up to only differ from each other by a transposition. But we've seen in the theorem before that the determinant of a transposed matrix is the same as the determinant of the original matrix. So this is the same. The determinant of F upper star is just the determinant of F, simply by this transposition property of the matrices. So this is basically a very concise summary of everything we did in this section almost, because this kind of, this is the really clean and neat version of this, by formulating this for endomorphisms. So these are the properties of the determinant for endomorphisms, and as I said, a proof with the references which theorem follows from which, so very precisely this is in the lecture notes. Okay. Okay, this was about endomorphisms, and in the next section we again get our hands dirty because we show how, or we will discuss how we can use the determinant to do really some computations. So really use computational methods and compute stuff. That is maybe, that's easier to compute than by other methods, and we will see how determinants then go in nicely. For example, when you compute the solution of the systems of linear equations, under some conditions you can use determinants instead of the Gauss elimination method, which might be slightly easier. So see you in that section.